So today we're going to look at section 2.2 of our exponential and logistics modeling. Modeling is just basically doing real world problems. That's what it refers to. When they do modeling, that means we're going to be doing using our equations in a real world scenario. So a couple things we want to know when they start talking about this. Population model. Here is a population model that we can use. Population P is changing at a constant rate R each year. Then I can use this model right here. And you can see that it's an exponential model. So this is the base number. There's your exponent. And this right here is the initial population. So they use this little P sub 0 means initial. So if you see a sub 0 on something, it usually means the value when the exponent is 0. It's the first number, things like that. So this is your initial population. R is a decimal. You want to use a decimal amount in there. T is time in years. And then the R. If that R value is greater than 0, then this represents an exponential growth function. And 1 plus R is called the growth factor. R is the growth rate, but 1 plus R is called the growth factor. If R is less than 0, which means it's negative, then you have a decay. That means you're going down in value. And then that would be your decay rate, and then 1 plus R is your decay factor. So when we do populations like that, and we'll do one here in a little bit, that's the model I'm going to use to fit into population stuff. There's another one called radioactive decay. So this is a decay process. The process where the number of radioactive atoms of a substance change to a non-radioactive state for a fixed function fraction per unit of time. And pretty much this is how that works. The time it takes a radioactive substance to change the state of half of its amount. So half-life basically means this, and then we'll talk about the formula here in a little bit. If I take 100 pounds of radioactive material and lock it in a vault, bury the vault, and let's say it has what's called a half-life of 1,000 years. If I come back after 1,000 years and open up that vault, then I will only have, I think I said 100 pounds to start with, I will only have 50 pounds of radioactive material left. The other amount changed into something else. Usually something not radioactive. Okay? But it could be the process for, that's all your chemistry stuff, you can look at that later. Okay? If I lock it up again and come back in another 1,000 years, then I will only have 25 pounds of the original amount left. Half amount again. And each 1,000 years, the amount cuts in half again. Okay? The other parts don't disappear, it just became something else. So in this formula, this is a half-life. R is the initial amount. R sub 0 is the initial amount. T is time in the same units as the half-life. And H, which looks like an N in here, H is the half-life. So it'll tell you it has a half-life of this many years. Okay? Or whatever the case may be. And so it's a half-life, so you're gonna have the one half is the base number. It diminishes by 1/2 each time. So when we do half-lives, that's what we're gonna be dealing with right here. So these two problems we're gonna look at, I got a couple of examples we're gonna look at on those. And then we have your logistics growth functions. Exponential growth is unrestricted. That means it just keeps on growing without bound. And that many populations don't really follow into that in reality. So over time, the logistics growth function is much better for population growth over a longer period of time. And it has what's called a maximum sustainable population. That means that is the upper bound, the top part of our graph. It's a horizontal asymptote, and in our logistics model we used last time, that would be the value of C. So these are what we're going to be looking at. I'm going to show you some different things with the calculator also. And don't forget that I gave you some new videos on how to use the TI Inspire calculator to find some of these things on the calculator from a table. So let's look at a couple of examples. I'm going to look at example number 13 in your textbook on page 265. And here's what number 13 is talking about. So they give us the initial height of 18 centimeters, and we have a growth rate of 5.2% per week. And we want to determine the exponential function that satisfies these given conditions. So we want to find the equation that we're going to use. Okay? So how do I do this? Well, this is a growth function. So we're going to follow that format right there. So I'm going to come over here. I'm going to write down my formula that I'm going to use so I know what to plug into things. And so we're in centimeters for our height, and our rate is in a decimal and per week. So our time element is in weeks. And so R is the growth rate. If this is a percent, I need R as a decimal. So we need to move the decimal point 2 places over. And so R is going to be 0.052. That is what your decimal form of R is. The initial height is 18. That's P sub 0. The initial height is 18. And so we want to plug this information into this formula. And our function for growth is going to be 18, 1 plus 0.052 to the t, and that is my equation right there. And then from that, we can determine what the height would be at different times. So if I ask you then to determine what p of 8. So since t is in weeks, this would be at 8 weeks. And notice, type it in another thing, plug it into our calculator. So 1 plus that is 1.052. And then you plug in 8. And then you can just use your calculator and you can approximate that answer out. And that's how that would work. So we grab our calculator. And we go 18 times, and then I would put a parenthesis just because 1.052 raised to the 8th power. Got a little glare there, but there it is. And if you hit Control and Enter, it'll give you a decimal. And so what is the height after 8 weeks? 27 to 3 decimal places, 002 centimeters. And so that's how I can do a problem like 13. I think they only wanted this part for 13, but I made up the other part, how I can then use it to predict something in 8 weeks. So radioactive decay, I want to look at problem number 33. In your textbook on page 265. So we have a half-life in 14 days. So the half-life is 14 days. Your initial amount, this is all information they gave you, is 6.6 grams. The first thing they want you to do is they want you to find me the equation for this. So our template, just like we did over here, we want to know what it is. So we write it every time to help us remember it. And then T over H, that's the half-life. T is in the same units as the half-life, and our half-life is in days, so T will be in days. And so we can just plug in our information into this equation. R of T, the initial amount, 6.6 grams, 1/2. T I don't know, but my half-life is 14, so this would be T over 14. So that is my formula. Part B is, when will there be less than 1 gram remaining? So when means I need to know a time, and I want 1 gram left. That means the amount left, that's what this is, the amount. I want that to be 1. So in doing this problem, it'll be 1 equals 6.6 times 1/2, and then T over 14. So as you know, we do not have the ability to solve this algebraically yet. So we would have to use our calculator technique for graphing and finding points of intersection. So again, we can come up here, open up a graphing window, graph this thing, type it in exactly as you see it. So it'll be 6.6 times parentheses, fraction. You got glare, you can't see anything. That's hard to read. Sorry. I'll show you after I'm done. You can do instead of 1/2, you can do 0.5. It makes it a little bit easier in the calculator. So I'll put 0.5, close the parenthesis, and then raise it up to, and then this one has to be a fraction. It'll be X instead of T because I'm graphing it on my calculator. And then 14. So I think I put a 5 in there. So instead of the 1/2, I put a 0.5, and there is the formula right there. I can hit enter, and it will graph it for me. I may not be able to see the whole thing yet, but I will change the window to see it. And then the next one here is I want to graph the second part of the equation, the 1. So I'll put it equals 1 and graph that. And I need to see where those two things intersect. And we can see it's going to be way over here somewhere. So I need to change the window to see where they intersect. So clearly I don't need any of the negative stuff over here or anything down below too much. And so I'm going to go into my menu. I'm going to go to my window. And I'm going to change my window. I don't need any of the negative stuff over here, so I can just make that a 0. Max, I don't know where to put it. But since we're talking about days here, and it's a 14-day half-life, I'm going to remove 5.6 grams of material. So I'm probably going to need to go out a little bit farther, clearer than 10. I don't know how far, so why don't I just pick a big number? Let's just try 50 and see what happens. That might be too far, may not be far enough. I don't need a lot of negative stuff. I do want some, so I don't want to go down to 0. So maybe just leave that alone. And then this one, we'll just leave it at the height of 6, and we'll just go from there. So the X was the only one that we need to really change. Hit OK, and it'll reposition this thing, and I can see it crossing right there. That's what I needed to see. So we go through the process for finding points of intersection. Again, menu, analyze the graph number 6. Intersection is 4. Move to the left of that point. I want to be on the left side. Then it changed to, let's say, upper bound. That means I move to the right of that. The dot will appear. And then we got to move this out of the way so we can see what the number is that we got. And you can just grab stuff and move it out of the way. And you can grab the point and move it over here. And we see that we get T is going to be 38.1145. That's what I have right here. So what does that mean? That's the point they intersected. You need to answer the question that they wanted. The question they wanted is, when will there be less than 1 gram remaining? when you write your answer, you should write it in a sentence, answering the question that they asked you. This is how you do real life scenario stuff. Don't just slap a number down here and expect me to know what it stands for. And units are also important. If you don't put proper units on your answers, you will lose points on a test or something. I will dock you for not having proper units. So when will it do? Be less than 1 gram. We will have less than 1 gram. 1 gram after 38 point, and then round this to 3 decimal places, so it'll be 38.115, and the units of measure are days. And that's how you should answer that question. For regression models that I made a video in your important information in the Google Classroom. You can go there and take a look at it. So I'm not going to include it in this video itself. So I'm going to end that video here. Those are the 2 examples. Kind of follow that out, and then we'll take questions outside.